Hello everyone. Today is the last of the 3-series lecture that I have been doing with the TJ AI ML Club. As you know, my name is Raj Dasgupta and I am with the Naval Research Laboratory. The title of today's lecture is AI-based game playing with reinforcement learning. Our objective today is to combine the topic of the last two lectures and see how they can be used to play large computer games. Now, in the first lecture, we had talked about game theory. If you remember, the main technique that we had learned to play games was called Nash equilibrium, which gave a stable solution that two players could use to find an outcome of the game. Then, in the last lecture, we talked about reinforcement learning. The output of the reinforcement learning algorithm was something called a policy, which basically gave the base or optimal action that an agent could take at every step or stage while trying to solve the problem at hand. Now, in this lecture, we will talk about how we can write AI or computer programs to play games on the computer. Games like tic-tac-toe, then chess, computer Go, and finally StarCraft 2, which is a pretty large and complex game. Now, a standard mathematical representation that's used to represent games is called a game tree. As the name suggests, it's a tree. The root of the tree corresponds to the first player. The edges coming out of that root are basically the actions that the first player can make at the start of the game. And the children of the root node are basically the move corresponding to the second player. And once again, as you might have guessed, the edges coming out from the level 1 nodes are basically the actions that the second player can take. So on this slide, on the left side, I am showing the game tree corresponding to chess. So the first is the white moves. Basically, there are 8 pawn moves and a couple of others like the knight move that the white can do. And for each of those moves, black will respond with any one of the moves, like pawn moves or knight moves that it can make, and so on. So like this, the tree keeps on growing. Now, I understand you all have studied AI-based search algorithms like breadth-first search and depth-first search. Okay. Now, these are basically exhaustive or complete search algorithms. They will go through the entire tree until they find the goal node. Now, as you can guess, game trees for games like chess are very large. And so if you want to go through all the nodes exhaustively searching the tree, then it would take an enormous amount of time and computational resources as well. So instead of doing exhaustive search, what is done is called a stochastic or probabilistic search. As the name suggests, probabilistic search means that you do not search through the whole tree, rather through all the nodes. Rather, you opportunistically or strategically select certain paths, certain nodes in the game tree to explore. And why are we exploring this tree? To see which moves would be good moves, which moves would result in a win for me. So now let's talk about one of the most popular probabilistic search algorithms called Monte Carlo tree search. Monte Carlo tree search has been used in computer AI algorithms like AlphaGo, also for other games like Rome 2, poker. It's also been used for medical applications like DNA sequencing and also for motion planning in autonomous vehicles. I understand many of you all might already know Monte Carlo tree search, so I'll keep this short and fast. I illustrate Monte Carlo tree search with the game tree for tic-tac-toe. As you can see in the game tree, at the root node, the first player, I consider the X player to be the player 1. The player 1 has 9 possible actions corresponding to the 9 cells in which an X mark can be placed. At the following level, it's the circle player or O player's turn, and the O player has 8 possible moves for each node at the level 1 level. And like that, the tree grows. Now, one of the issues in game trees is that you do not know who is going to be the winner until the leaf level or the terminal level of the tree is reached. So when you get to the terminal level, the full board is available to you. You know which player has placed a mark where, and depending on the state of the board, you can assign who is the winner. Okay. So here I consider a win for the first player, the X player 2 correspond to +1, draw to 0, and a loss to -1. This is an instance of a zero-sum game, which is a win for player 1 equals to a loss for player 2 and the other way around as well. Now let us see what the problems of a Monte Carlo tree search is. Now we'll assume that in tic-tac-toe, the computer player is the first player, which is player X. Now as the computer A starts to play the game from the root of this game tree, the decision that it has to make is which of those 9 possible actions, which branch should it go down towards the bottom of the game. The problem is at the top of the game, the AI does not know which of those branches is leading to a win. So Monte Carlo tree search solves this by playing this game in simulation. Okay? It generates the game tree, and then at the bottommost level, it sees which of the game states are leading to a 0, draw, a win, +1, and so on. And then it percolates these values or back propagates these values towards the top. That is what I'm showing on this slide. As you can see, the leftmost branch at the top is labeled a 0, and that 0 comes from down under. And similarly, the rightmost branch is labeled a 1, and once again, that value of 1 is back propagated from the leaf level. Now what Monte Carlo tree search does is, it does this back propagation, but it does not expand the whole tree. There are other algorithms like min-max tree search, which you might have heard of. Again, alpha-beta pruning, which you might have heard of again. Those expand the full tree, or maybe a smaller version called the pruned tree. But what Monte Carlo tree search does is it expands only certain branches of the tree probabilistically. These are the 4 steps of the Monte Carlo tree search algorithm. The first 2 steps, selection and expansion, basically tell how to select a node while traversing the game tree, and how to create a child node from the currently selected node while traversing the tree. These steps are identical to the steps in depth first search, breadth first search, or A-star search algorithm for selecting and expanding nodes while traversing the tree. The last 2 steps, simulation and backpropagation, are unique to probabilistic search algorithms like Monte Carlo tree search. The simulation step is also called rollout, and here a random walk is done from the currently selected node all the way down to the bottommost level of the tree. On reaching the bottommost level, the rollout or simulation step stops. Now remember, the bottommost level has the value or the outcome of the game. So in the backpropagation step, what is done is, this bottommost level node at which the rollout has terminated, the value is taken from that and is percolated all the way up towards the root of the tree, like we had said a few slides ago. Here is a picture that shows the 4 steps of the Monte Carlo tree search algorithm. The leftmost picture is the selection phase. The darkened node shows the path that's been traversed till this point in the diagram. Now as you see in the selection phase here, I am at this node. So now I have a choice whether I want to go down the already expanded child node out here, or whether I want to see whether this node has any other children nodes under it. So this decision is called the explore versus exploit choice. Exploit means I go down one of the already explored children nodes, whereas explore means I see if there are any other children which have not yet been expanded, and then I expand that children. So basically I'm doing an exploration down a path along the tree that has not yet been explored. Okay. Now if I choose to do exploration, which is go down a path that has not been explored, then I have to create a child node, and that is what is done in the expansion step by creating a child node. Okay. Now note that after I've done the expansion here, my search is currently at this node, the darkened node out here. Okay. And now this node does not have any children under it, so I don't have a choice of explore versus exploit, because there are no other children under this node to do an exploit from. So that's why the only thing that I can do to go downwards from this node is to do a simulation or a rollout step. And as I said, the rollout continues all the way towards the bottommost level. It stops there and then starts the backpropagation phase, which it takes the value from that bottommost state and it percolates it up or moves it upwards towards the tree. But remember that the random walk or rollout path that was created is not maintained anymore. Rather, the backpropagated value is only updated along the nodes of the path going up towards the root of the tree, those nodes which had already been expanded. So this is the flowchart of how the Monte Carlo tree search algorithm works. As I understand, you have looked at Monte Carlo tree search before, you have worked with it, so I will not go into the details of this. So this was a quick overview of Monte Carlo tree search. There are many resources available on the internet. I've given some of them there. Now the reason why we were looking at Monte Carlo tree search is because it is an integral part of computer AI algorithms like AlphaGo, AlphaZero, and so on. Next, what I would like to do is to talk about some of these AI game playing algorithms. And these algorithms integrate the Monte Carlo tree search, like tree search algorithms, game tree search algorithms, along with deep learning. So we'll review 3 recent algorithms which are built one on top of the other. So the first algorithm is AlphaGo, which came out in 2016. You might already have heard its name. It's very well known. It uses deep learning along with game tree search in order to play the computer game Go. And subsequently, it was extended to play any game beyond Go, and a couple of extensions were also made, and that is the algorithm AlphaZero. And finally, last year in 2019, the AlphaStar algorithm, which is an improvement on AlphaZero, came out, and that was specifically meant for playing the StarCraft 2 computer game. Now let us see each of these algorithms and review what the main aspects of these algorithms were. We start with the AlphaGo algorithm. Okay. So the key ideas are this, that like any computer game we have been talking about, the game Go also has a lot of states, a lot of actions. So basically the search space is enormous and you cannot afford to do an exhaustive search. Okay. But the problem is that the search space is so large that if you just use the raw probabilistic search algorithm like Monte Carlo tree search, then also you don't expect to be able to play against a human computer, which is basically you cannot take decisions in real time, or even if you pre-compute, the pre-computation time will be so large that it will not be practical to solve. Okay. So what researchers proposed is we have to find a way to reduce the search space. Reduce the search space both in terms of the breadth and in terms of the depth. Now let's think a bit, where does the breadth of the game tree come from? Remember, at each node, the number of decisions or the number of actions, in other words, the number of edges that were going out of that node, were basically the number of possible actions at that node. And if you think of the picture of a game tree, the number of actions that you have at a node is basically contributing to the width, the breadth of the tree. So if I want to reduce the breadth, I somehow have to curtail the number of actions. So basically this is the idea that's taken in AlphaGo. So to reduce the breadth, what is done is we limit the number of possible actions from state S. By limit, what we mean is we choose those actions which are likely to lead to a win. But then you might ask, how is it different from what Monte Carlo tree search was doing? Well, the difference is that we not only train this on possible winning actions from Monte Carlo tree search, but we also use deep learning in order to look at past games, past human gameplays played by human champions, and see which were the moves those human champions make. And we train the algorithm with the moves of those human champions. Okay. So basically what the way this is implemented is we try to see how many times a certain action was taken from the current state S. If the action was taken very few number of times, then we don't go down it, saying that it was not a good move. None of the past humans have taken it, not even Monte Carlo search is proposing it. So we just discard that action. So this is how the pruning or the removing of the actions from a node is done. This is represented by means of the probability value given there. So probability of taking action A given the current state is S. And this is represented by a function of G of S. Okay. This G of S is learned using a combination of supervised learning and reinforcement learning. It uses a deep neural network. It has 12 layers. The supervised part is trained with moves from past human games, like I was mentioning. It was trained over 160,000 games and 30 million possible states. Just to give an idea how long it took 4 weeks to train on 50 GPUs. So enormous computing power was used. And after the supervised learning was done, then the reinforcement learning part was done. And basically what reinforcement learning part does, it exploits a technique in game theory called self-play, which is the agent or the AI builds a model of itself and it engages in play with that model of itself. Okay, and where does the AI get this model from? Basically, it does a little bit of reinforcement learning, comes up with a certain policy, freezes that policy, uses it as its current opponent. And then the AI continues to implement the reinforcement learning, do the policy update and so on, while playing against the frozen policy that was there. So this is how the reinforcement learning works. And the reinforcement learning part was trained for 1 week on 50 GPUs. So basically this is a picture representing, giving a very high level overview of how the AlphaGo breadth reduction works using this function g of s, which is probability of a given s. So basically you have the current state. So this is your s. And so what you want to predict is the best action to take at this state. So you use the prediction model, which is a deep neural network. Prediction model basically calculates g of s, which is essentially a probability of the different actions that are possible from state s. And then it selects the action which corresponds to the highest probability value here. And that is the most probable or best action, most probable action taken by past humans. And that is the action that is selected. So basically what you end up having is from the current state s, you do not have to select from all the actions, but you only have to select from a small set of actions which have high probability values, and also you select the action which gives the maximum probability from those. So basically this is how breadth reduction is done in the game tree of AlphaGo. The next step, once we've reduced the breadth, is to see whether we can reduce the depth or not. Okay. So the depth reduction is done by estimating the value of the state S using a value function, also called a board evaluation function. This V of S is a real number which lies in the range of 0 and 1. 0 corresponds to a loss and 1 corresponds to a win. VS is learned using regression learning with stochastic gradient descent. Once again, it uses a 12-layer convolutional deep neural network, and the training was done with 1 week on 50 GPUs. So basically at the end of this, what you have is given a state, it assigns a value to the state. If you recall, this is very similar to what reinforcement learning, or one of the aspects we had in reinforcement learning, which is with Q-learning, we were calculating the value of a certain state. And this function does exactly that by using a deep neural network. So how does this achieve depth reduction? Basically, at a certain state, you see what the value of the state is. If the value of the state is low, then you do not go down that state anymore. You abort the search down that tree and you explore another part of the tree. You go back upwards and you come down another path of the tree until you find a state whose value function is high enough, which is close enough to a win. So now we have achieved both our objective, which is breadth reduction and depth reduction. So this is what a schematic of the different steps that are used to play AlphaGo is used. And finally, once we have this, then comes in the piece that we have looked at, which is we have to now play the game. But now we are not playing it on the full game tree, but we are playing it on the reduced game tree, where we have reduced using this combination of policy network and value network. And to play this game, we use our old friend, Monte Carlo tree search. And we start from the current state and we virtually play the game till the end of play. Basically the way probabilistic tree search and Monte Carlo tree search works. So in this way, you can calculate or you can find out what the best moves are within a very large state space, for example, like the computer Go algorithm. AlphaGo was proposed in 2016, and then researchers of DeepMind, the company that worked with AlphaGo, that came out with AlphaGo, they continuously kept on improving the AlphaGo algorithm. If you look online, you see there are different flavors of AlphaGo that are available. They are named after the different grandmasters they defeated. So there's one called AlphaGo Lee, AlphaGo, I think Fan Hui or something like that. Basically, whichever grandmaster the algorithm defeated, the algorithm was named after that. And incrementally, they started doing better and better. Okay. Now, the AlphaGo algorithm was written only for playing computer Go. And so then DeepMind researchers started looking at how can we generalize this algorithm to play other games, for example, chess and shogi. Okay. And so at that point, they came up with a new algorithm, which is called AlphaGo 0, and it's non-Go versions for playing chess and shogi were just called Alpha 0. The reason why the name 0 is used in the suffix there is because one of the main changes that they did here was they did not use too much of the training data from past gameplays. Remember the expert gameplays we had said, which were used to do the training part, that was not used that much. So here they entirely use self-play. So on this slide, I have shown what the differences between AlphaZero or AlphaGo 0 and the regular AlphaGo was. So as I said, it uses only self-play as opposed to supervised learning and training from past moves. Instead of using two networks, one for the policy part, another for the value part, it uses a single deep neural network. And also a simpler tree search than Monte Carlo tree search rollouts is used. And finally, hyperparameter tuning was not used in the AlphaZero version. And as you can see, if I remember correctly, the amount of training that was required for AlphaZero was also lesser than AlphaGo, which required 4 weeks on 50 GPUs and so on. So here are some graphs which show for different games how AlphaZero does as compared to other standard algorithms. So for example, let's look at chess. So the y-axis here shows what is called the ELO rating, which is a standard rating that is used for games. And one of the best chess playing engines you might have heard of is Stockfish. And this is how AlphaZero compares to Stockfish. As you can see, in about 200,000 or 150,000 steps, it achieves comparable performance. Similarly, for Shogi, AlphaZero actually outperforms the best AI algorithm Elmo that was there. And finally, for computer Go, here we show AlphaGo, AlphaZero, and AlphaGo Lee, which was the AlphaGo algorithm that beat Grandmaster Lee. And as you can see here, AlphaZero slowly learns because it's doing self-play, so it does not go right away to the best possible. Whereas AlphaGo and AlphaGo 0, they are flat because they do the supervised learning part, and that is not shown in the graph here. But the main thing to show out here is AlphaZero, despite not using supervised learning, training via supervised learning, it's able to achieve comparable performance in about 400,000 steps. So this was a big step, which is basically, what is it saying? It's saying that the AI, without having any previous information, without knowing how to play the game beforehand, just by playing with a model that it has built itself, just by self-play, it's able to learn to play the game, and not just learn to play the game, learn to play the game at the grandmaster level. So this was a big step in the AI-based computer gameplay world. Okay, this is a graph that shows the comparative comparisons of the different alpha flavored algorithms we looked at, AlphaGo, AlphaZero, and the different intermediate algorithms. And you can see incrementally it kept on improving, AlphaZero being the best. Finally, let me talk a bit about the last algorithm that came out from DeepMind, which is AlphaStar. Okay. As I was mentioning, this is an algorithm for playing the AI game called StarCraft 2. Many of you might have already played the game. Some of you might be familiar with the algorithm that's used for playing StarCraft 2. So the game of StarCraft 2 is a bit different from computer Go, chess, and so on. The reason for that is, in chess, it's what is called a perfect information game, and same for Go. And what is a perfect information game? Perfect information game is where at each step, each player can see the state of the board and also can see the move that the opponent has made. For example, if I'm playing chess, I can see the chessboard, and when I'm about to make a move, I have just seen the move that my opponent made. And not just the current opponent move or what the opponent just moved, I have seen the history of moves that the opponent has made. So basically, knowing the opponent's history of moves, and of course knowing my own history of moves, makes it much easier for a game tree algorithm, for an AI algorithm working on game trees, to find out what is the best move. Now that is the case of a perfect information game. In contrast, if you have an imperfect information game where you are not able to see the opponent's move, can you think of an example of an imperfect information game? Well, there's a game called Battleship. You might have played as a child, or might have played on a computer as well. Battleship, you remember there are two boards on which you set ships. You set a set of ships on your board, and your opponent sets up a set of ships on the board. And then you have to call out XY coordinates and fire at that location on your opponent's board, and your opponent says whether it's a hit or a miss. That is an example of an imperfect information game. Imperfect information because you are not able to see where the ships on your opponent's board are. Okay. And so StarCraft 2 is an example of an imperfect information game, because there is a setting called Fog of War, which basically means that you are only able to see the game pieces which are within your sensing range. If it is outside your sensing range, you cannot see anything. So basically you have imperfect information at that point. So this makes it more difficult to play the AlphaStar game. And once again, so as I was saying, you have partial observability here, you have imperfect information here as well. And finally, you have a large action space. In fact, this is much larger than chess or computer Go. Okay. So the main algorithm is basically our AlphaZero algorithm, but in this, DeepMind introduced a technique called league play. So league play basically extends self-play, but now because you have multiple players, it's self-play between multiple players. And these players are still organized in two sides. You have the friendlies and you have the opponents, but still it's between multiple players. So these two sides are called the teammates or agents versus the opponents or the competitors. Okay. I will use the language they have used in the paper, which is friendlies are called agents and there are M agents, and the opponents are called competitors and there are N competitors. So these agents learn a policy via policy update. So the specific algorithm that they have used there is the asynchronous actor critic, A2C algorithm, which we saw in our last lecture. On the other hand, the competitors have a fixed policy. Remember, this is again self-play. So basically the competitor is a model of the competitor. Okay. And how are these competitors spawned, or how are these competitors built? Basically from time to time, the best agents that are playing the game while doing the reinforcement learning, those are frozen. They morph into the competitor, into the opponent side. And basically this ensures that if you're playing with an opponent which you yourself were a few steps ago, which is basically one of your ghost opponents, one of your ghost selves from the past, basically you are as good as that opponent if you learn to play against that opponent. So basically it ensures that agents remember to play against some of the best opponents, their past selves. The AlphaStar algorithm made two important contributions. The first was a technique called Prioritized Fictitious Self-Play, or PFSP for short. Prioritized Fictitious Self-Play had two underlying techniques. The first one was called matchmaking, which ensured that when you pair an agent with a competitor, you make sure that their expertise levels are commensurate with each other, which is you do not pair up a novice agent with a very expertly playing competitor. Other technique that was used was exploiters, which is basically some competitors which gave very hard game levels for the agents to solve. The objective was to identify the weaknesses of the agents. And so if the agent played against these exploiter competitors, they could discover their own weaknesses and overcome them. And then in one of the versions of AlphaStar, the researchers realized that some bootstrapping, basically providing some human gameplay data like they did in AlphaGo, would speed up the learning process. So this is a timeline which shows how the different versions of AlphaStar subsequently improved in the scores that they got. Now I'd like to talk very briefly about sequential games from game theory. Here I'm showing the picture of a sequential game, and as you can see, it has a tree structure. So one of the techniques that can be used is to convert this tree structure into a matrix-like structure and then use Nash equilibrium-like techniques like we had done in the past. There's some problems with this, which is basically it makes the space, the size of the matrix, it exponential in the number of actions that the two players had. So basically there are time complexity and space complexity issues. And another problem is all the Nash equilibrium are not real Nash equilibriums. In other words, they might not happen in reality, although they exist in theory. So essentially a technique which you called subgame perfectness is used to check whether it's a real Nash equilibrium or not. And an algorithm called backward induction is used in order to find these Nash equilibrium algorithms in sequential games. So now this is a deeper topic, and I have given some slides which get into more details of this, and there are textbooks too on this. But for the sake of time, I will keep this shorter. Now coming back to AlphaStar. Now one of the things that they did in AlphaStar, which we have not talked about till now, which is instead of using the UCB1 metric for doing the explore versus exploit choice, they used Nash equilibrium in order to find out what the best action of each player was going to be. So this basically represents the confluence of the game theory based techniques that we have been talking about and the reinforcement learning and AI game techniques that we've been talking about. So AlphaStar basically exploded this field. So a lot of research started working, mainly because AlphaStar showed that you could make an AI learn from scratch how to play an imperfect information game. This was very important because chess and Go, those were all perfect information games. Whereas StarCraft was an imperfect information game. Very important because in real life, especially in competitive scenarios, like the ones we look at in the Navy or in the DoD, or even if you look at any general competitive setting, you don't expect to know what your opponent's move are going to be. So if you can decide your own winning move, find out your best action without knowing your opponent's move, that would be a game changer. Basically, you can apply that to a lot of scenarios, and if you can defeat humans, play superhuman level, then that's very good. So that is where a lot of activity in game playing AI is going on. So after AlphaStar for playing StarCraft 2, there has been very recent research for playing Texas Hold'em poker, which is also an imperfect information game because you cannot see the deck of cards, the hand that your opponent has. And there's an algorithm called Deep Stack. You can look this on the internet. Deep Stack was used to solve Texas Hold'em poker. Another game called Hanabi is there, which is also an imperfect information card game. So now there's a lot of research activity. So this is basically the cutting edge of game playing research, which is how to come up with AI algorithms that can play imperfect information games. And my research group at NRL works exactly in this area, how to use reinforcement learning along with game theory to solve imperfect information games. So at this point, I would like to wrap up the lecture, giving a summary. So what we saw in the first lecture was game theoretic techniques for small games, 2-player games, each player had 2 actions, but we found out how to solve the game using Nash equilibrium. So the limitation of traditional game theory is it applies to rather small settings, 2x2 games. Okay. Then in the second lecture, we looked at deep RL techniques, deep reinforcement learning, different algorithms like deep Q networks, actor-critic learning, and so on. And finally, today, we looked at how to use AI-based gameplay. We mainly looked at algorithms like tree search algorithms, then AlphaGo, AlphaZero. But then in AlphaStar, we saw that there's a coming together of the Nash equilibrium and the AI-based gameplay, reinforcement learning, and all the other things that are there. So that brings us to the end of this 3-part lecture. I've tried to cover a lot of topics. Once again, the slides are all with you. There are many topics inside this. Feel free to research on this on your own. If you're interested to delve a bit further into this, feel free to ask me. I can be reached by email. I'm always there, happy to help. And once again, I would like to remind you, for high school students, NRL is very interested to receive CAP applications. I talked about that in our last lecture. I put up the slide once again here. I hope you have enjoyed this series of lectures, and I hope to hear from you soon.